This is the electricity homework booklet question 16, and we've got a question about a cordless phone handset containing two rechargeable cells connected in series. The cells have got an EMF of 2 volts, and when fully charged, combination stores energy sufficient to provide 850 milliamps for an hour. We've got to calculate the total energy stored by the two cells when fully charged. I went with W because IVT. You could work out the power, then multiply it by time, but that's of course exactly the same thing because the power equals IV. Multiply that by the time, 850 milliamps. I went with 2 volts, and 1 hour is 60 times 60 seconds. That gets me to an energy per cell of 6120. Getting that gets you the first mark, that gets you the second. But because I've got two cells, I've got to double that up for there. Alternatively, and perhaps arguably better, you could actually do the same thing but use the total EMF for the two cells in combination, which would have been 4 there in that place. Would have taken you straight to the 1.2 times 10 to the 4 joules. Internal resistance of each cell is 0.6 ohms. Calculate the potential difference across the two cells when they're connected in series across a 20 ohm load. So we've got to just think about what's going on in total. Series circuit, so the total internal resistance is 1.2 ohms and the total EMF is 4. The EMF is I, brackets R plus little r, internal capital R plus lowercase r, internal resistance. So I is the total EMF over the total resistance for 20 external plus the total of 1.2 internally, gives me that current. If I then look specifically at the 20 ohm resistor, do a V equals IR calculation, 0.189 times the 20 ohms, 3.77 volts. Two significant figures because that's what my data is, gives me 3.8 volts. So the mark distribution there is recognizing the total internal resistance is 1.2 ohms, calculating the current for the second mark, and then the PD for the third. So that's the electricity homework booklet question 16.